Question 1. Draw the shear and bending moment diagrams for the beam and loading shown, and determine the maximum normal stress due to bending on the transverse section at C, which is this one. And from the problem, it is known that the beam is wide flange 460 times 113. So the strategy to solve this problem is, first, we need to find the reaction forces at A and B, and next is do the sectioning for every point at the beam A, C, D, E. The next is draw the SFD and the BMD of the beam, and the last is use the biggest bending moment to calculate the maximum normal stress. To start our analysis, we need to determine the reaction force at A and B. In here, we draw the FBD, which is, it could be seen that at A it is a pin and at B it is a roller. So they have this kind of reactions. And at C, for the transverse section, we could redraw it into an equivalent force equal to 216 kilonewton. In here, to start our analysis, we could take the sigma moment at A, which is equal to this one, and we could obtain the RB equal to 279 kilonewton. And next, for sigma Fy, we could obtain the Ra, which is equal to 237. And next is for the sectioning part. In here, we could cut it first after A, before C, after C, before D, after D, before E, after E, and before B. And then for the sectioning part, we could begin from the after A section. In here, there is only one load, which is Ra, reaction force at A. So V1 is equal to 237 kilonewton, while the M1 it is equal to 0 because this reaction force at A has a really small distance, which we could assume it to be equal to 0. And then before C, we have two forces, which this transverse load is replaced by an equivalent load equal to 216 kilonewton, which is obtained from 19 times 2.4 meter. In here, V2 is equal to this one minus this one, which is equal to 21 kilonewton. And for the moment at 2, it has the distance from Ra and the distance from this equivalent load, which for Ra it is 2.4 meter, and for this transverse load, the equivalent one, it is placed right in the middle of this transverse section, which is equal to 2.4 divided by 2 equal to 1.2 meter. So the moment 2 here equal to 309.6 kilonewton meter. The next is after C, which almost the same because the distance is increased a little bit, but we assume it is the same distance. So we will have the same moment and the same V2. Next is before D. In here, we still have the same two force, so V4 is 21 kilonewton also, but the distance already increased a lot, which is added by 0.8 meter. So this 237 is multiplied with 3.2 meter, and for this equivalent transverse load is multiplied with 2 meter. So we have M4 equal to 326.4 kilonewton meter. And then for the sectioning right after D, we have these three loads, this one, and this one. So we have V5 is equal to 237 minus 216 minus 150 kilonewton. So we have V5 equal to minus 129 kilonewton. And for the moment 5, we have this one times resistance of 3.2 meter this one also minus 2 meters for this one. And for the 150 kilonewton, we assume it to be 0 because it is really small. So M5 is equal to 326.4 kilonewton meter. And the next is before E, the load is still the same. So we have that V6 equal to minus 129 kilonewton also. And for M6, the distance is different, which is 237 kilonewton times 4 meter, and this 216 kilonewton times 2.8 meter, and this 150 kilonewton times 0.8 meter. So we have M6 equal to 223.2 kilonewton meter. The next is for after E, the load is now increased. We have 4 loads in here, which V7 equal to 237 kilonewton minus 216 kilonewton minus 150 and 150 kilonewton. So V7 equal to minus 279 kilonewton. And the next is for M7, which the distance is the same, while for this new load is assumed to be 0 because the distance is really small. So M7 is equal to 223.2 kilonewton meter. And the last is before B. In here, still the same 4 loads, so Vx is also equal to minus 279 kilonewton. While for the moment, it is the distance is increased. Now 237 times 4.8 meter, and this equivalent transverse load is equal times 3.6 meter, and this 150 kilonewton is times 1.6, and another 150 kilonewton times 0.8. So we have M8 is equal to 0. And now, since we already obtained all the shear force and the bending moment of the beam, we could draw the SFD and the BMD. For the SFD, at A, we have RA, which is equal to 237 kilonewton, and from A to C, we have a transverse section which decreases this load into 21 kilonewton. And at D, it has a downward force, so it decreases into minus 129 kilonewton, and at E also, it decreases into minus 279 kilonewton. And at B, we have RB, which is equal to this value, but it is going up, so at B it will be 0. And the next is for the BMD. For section A to C, there is a transverse section where the load is based on the distance, so the bending moment will form a curve like this one, where the maximum value of the transverse section is equal to 309.6 kilonewton meter for the bending moment. And for DEB, it is a normal load. At D, the bending moment increases to 326.4 kilonewton meter. At E, it decreases to 223.2 kilonewton meter. And at B, it is equal to 0. And the next is, from the problem, we know that the beam have a code of W460 times 113 for the y planes, and we could obtain S from the appendix is equal to 2390 times 10 to the power of 3 millimeter cubic. And then this is the formula to calculate the normal stress from the bending moment. Since the problem asking the maximum normal stress at the transverse section C, so we will use this bending moment value. Substitute the value into the equation, and we could obtain that the normal stress, maximum normal stress at C is equal to 129.54 megapascal.